Okay, so we have finished till now the first law of thermodynamics, second law of thermodynamics, both from classical and statistical approaches, and we have seen that for a spontaneous process, for an isolated system, entropy always increases. So, which means that either we consider something like an universe beyond which nothing is there and energy is conserved within that, and all processes within that universe will be spontaneous because and entropy will increase, or we consider whatever the system it is, for example, a glass of water or bottle of water, we take into account of the surrounding as well, and then together the entropy of the system and surrounding has to increase for a spontaneous process. Now, let us say if we did not want to look into the surrounding at all, let us say we want to only look into the system and try to identify whether the process will be spontaneous or not. In that case, we cannot rely only on the entropy of the system, because we have seen many times, especially for let us say transfer of heat from one part to another part, that entropy decreases for subsystem, and then entropy of the other subsystem increases, and together the entropy increases. So, therefore, if you look into only the system, then entropy is not the criteria to talk about the spontaneous processes. So, there are new things called free energies, which you may be already familiar with, are introduced in order to see whether the process is spontaneous or not, and we will get into that today. So, today we are going to look into ways of only looking into the system and then find out whether the process is spontaneous or not. So, for that we will introduce something called fundamental equation of thermodynamics, and also we will combine the first law of and second law and introduce new properties, new calculation, new properties, new thermodynamic potentials. So, let us start with what you already know. So, let us start with first and second laws of thermodynamics. So, what is the first law? So, first law says that du is equal to dq plus dw. So, you know that this cut here denotes the process is path dependent, whereas du is a state dependent property, and you also know that the process can be reversible or irreversible, does not matter, d will remain the same. So, we can write for a reversible process as dq reversible and dw reversible. What the second law says? Second law says that ds is dq reversible by T. T is the temperature of the system, and dq reversible is the reversible change in the heat. Remember that often we have found out that dq is 0, but dq reversible is not 0 for some systems in an isolated case. For example, we talked about the free expansion inside an isolated system, and what we saw there is that since the system was kind of isolated, our system was isolated, there was no change in the heat. So, dq was 0, yet we found the entropy was increasing because dq reversible was not 0, and that dq reversible essentially means that if you take the process in a reversible manner, then it would not be 0. Or you can think of in a different way, that although the dq was 0, but the surrounding entropy was not 0. So, but since we are talking about an isolated system, we are not talking about a surrounding entropy that time, because there was no heat released to the environment. So, therefore, we always have to construct an equivalent description, equivalent path going from a part of the system to the full part of the system for a free expansion, and there we found that for a reversible process the dq will not be 0. So, entropy, whenever we want to calculate, we have to always calculate with dq reversible and not with dq. So, that is an important point. Now, combining this above two equations, equation 1 and equation 2, what we get is that du okay. So, from here we can get Tds is equal to dq reversible. So, now combining the two equations, we get du equal to Tds plus dw reversible, and we know that TdS is nothing but PdV. So, du equal to TdS minus PdV. So, here you see that U, T, S, P, V are all state dependent property. So, given any state, you will be able to calculate these properties. It does not depend how we have arrived at that particular state. For example, whatever state it is, you know the internal energy of the system, because it depends only on the configurations of the system, and then similarly temperature, entropy, all are state dependent quantity. So, this equation is valid for any process, reversible or irreversible, it does not matter. So, now the fundamental, now we will introduce the fundamental equation of thermodynamics. Fundamental equation of thermodynamics says that U, which is an internal energy, is a function of S entropy, V volume and N. So, note that here it only says that it is dependent on this quantity, it does not give you the type of functions. It only says that it depends on this. For example, if I say that I have a function f that depends on x and y, I do not specify what is the nature of dependence. F x y could be x square into y, or it could be x y cube or simple x y, it can be any of these forms. So, therefore, I do not specify the exact functional form of u with respect to S, V and N. It only specifies that it depends on these three quantity, which also means that given these three variables S, V and N, one can uniquely identify the value of u. So, that is what that's all meant by this particular quantity u, this particular equation, fundamental equation of thermodynamics. Now, you know that for any multivariable quantity, so whenever there is a change in that variable, then it depends on the changes of the individual quantity. For example, if I want to talk about the changes in f, which is called total differential, don't be alarmed by the name. Differential is a change of in a small amount, and total differential means that whatever is the change in that particular amount f, which is df, but that change can happen either by changing the x or by changing the y or by changing the both, and that can be written as their partial changes. For example, change in f with respect to x when the y is constant multiplied by dx, or it could be change in y, change in f with respect to change in y at a constant x multiplied by y. So, you can notice that here f is a two dimensional variable. For example, if I talk about f as a height of a mountainous area, then you have to specify both x and y in order to talk about the height. Imagine a Google map, and if you put it in the height information there, you will see that in the map which has both x and y, you will see certain regions the height will be higher or certain regions height will be lower. So, there depending on x and y, you can always get that height. It does not matter how you go to that particular point, either you can go along x and then along y, or you can go along y first and then along x, or you can go both by changing x and y. Ultimately, if you reach that particular value of x and y, you will get the same value of height in the map, and that is what is meant by exact differential. We will come to that later on, but it only says that, let us say if you talk about only one variable. So, in case of one variable, what happens is that let us say our f would be just function of x, then this quantity will become df equal to del f by del x, because there is only one variable, into dx, and see dx will cancel, giving you df, or here del f will not be there because it is not a partial derivative. So, it will be just simple df by dx into dx, giving me df. So, if it is just function of one variable, then what we say is that the change in the value of the function is the slope multiplied by the change in the variable. So, slope is df by dx multiplied by the variable will give you the value. just like that happens for a single one dimensional case. However, if you have a two dimensional system, where you have specified x and y, and if you want to go from here, so you can go either this way and then this way, or you can go this way and then this way. So, let us say this point is x 1 y 1 and this point in x 2 y 2. So, either you can change x 1 to x 2 keeping y 1 fixed, and then y 1 to y 2 keeping x 2 fixed, or you can go this way and that way, this way and that way, or you can go this way. That is what I was mentioning earlier. Imagine this is just a map and we are talking about height of the points, let us say p and q. Similarly, here we are talking about u, which is function of three variables s, v and n. So, therefore, the change in u or total differential u can be written as their partial derivatives with respect to all those three quantities. So, I can write del u by del s for a fixed v and n into ds, ds is change in the s, plus del u by del v at a constant s and n dv, plus del u by del n at a constant s and v dn. These constants are absolutely important, because unless we put them constant, we are not going to do anything. So, remember what we are doing here, essentially we are not taking this particular path, we are taking this path and then this path. So, we are keeping one variable fixed and going in one direction, and then we are keeping the other variable fixed and going in that direction in order to make a change in the u or make a change in that particular function. So, here also we are doing the same thing. So, now you see, if I now compare this particular equation, so let us call that equation as equation number 4, let us call that equation number 4, and let us write down again equation number 3, which was du equal to TdS minus PdV, and third part was not there because we are talking about only two variables, but I can tell you for now that the third one, if we wrote, then it would be plus mu n. So, this one I did not mention before, because we are only talking about one component system. It will only appear for multi component system, that means when there are more than one type of component is present. Let us say we will talk about a mixture of A and B, then it will be there. If there is a mixture of more than two components, let us say 3 or 4, then also it will be there. So, in those situations it will be there. Now, let us compare the equation number 3 and 4, and what we observe? We see that this one, they are similar, because if I just take the ds out, then we get to see this one. Similarly, we see that this is same and this is same, we see that, right. So, then we can write that T is nothing but du by ds at a function v and n, and minus p is du by dv at a function s and n, and mu is du by dn at a function s and v. So, you see that we get three different quantities, and all are all these things are called equation of state. So, you can see equation of state, remember our PV equal to nRT for ideal gas equation of state, I could have written as nRT by V, and this P equal to nRT by V resembles this particular equation P equal to minus du by dV at a constant s and n. So, basically we are talking about the same thing, minus du by dV is nothing but nRT by V for ideal gas. So, you see interestingly here, first of all we get that by taking the derivative of u. So, that means the equation of state is derivative of the fundamental equation. So, equation of state is derivative of the fundamental equation. So, fundamental equation has all information about the system. However, when you take a derivative, you lose information. For example, if I give you a function f equal to x square. Now, if you take a derivative, you get f derivative of f will be as 2x. So, let us say if I give you f x equal to x square, the derivative of x you get as 2 x. If I give you f x equal to x square plus c, then also you will get f x as 2 x. So, and c can be any different values. So, therefore, for multiple different values your derivative can give you the same value. Derivative loses information. Derivative is something like a projection on that particular variable. For example, when you go from 3 dimension to 2 dimension. So, for any different heights you get the same line on the floor when you project on that. When you, so this is called projection. This is like a shadow that comes. So, when you project on this you get the same value irrespective of the height of this particular plane. So, you lose information. Similarly, equation of state does not have all the information because it loses information whenever you take a derivative of the fundamental equation, but fundamental equation has all the information. However, we do not know the functional form of it. So, therefore, we do not know, and the functional form will change with from one system to another system. So, therefore, we will not know unless, but we know how they vary with respect to the variable. Another important point of the equation of state is that they are all intensive variables. I have discussed about intensive and extensive variables long back. If you remember that intensive variables are variables that do not change with the size of the system. Since we are taking in the derivative, and if you notice that in these derivatives we are taking derivative of 2 extensive variables. For example, if you look at u and s, they are both extensive variables. So, when 2 extensive variables are divided, then essentially we give rise to an intensive variable. Similarly, look at p, there also it is ratios of 2 extensive variables u and v, and when you talk about mu, that also ratios of 2 extensive variables u and n. So, therefore, mu, t and p all are intensive variables and they do not change with the size of the system. Okay. So, now we got the 3 quantities. Another interesting thing you notice, which we talked about briefly while talking about statistical thermodynamics, that the temperature is nothing but change in u with respect to change in s. So, it means that whenever there is for a fixed volume of course and a number of particles, whenever there is a change in entropy there will be change in energy. So, it is a monotonically increasing function of entropy is a monotonically increasing function of energy, because I can write 1 by T as del S by del U. So, if U changes, S changes, and we saw that in case of let us say a particle in a box system, where whenever the energies were increasing, then the number of possible particle in 3D box, number of possibilities or number of degeneracies or microstates were increasing. So, that is very simplistic example of showing you that if the energy increases, then the number of possibility increases, and that was another reason that we talked about when heat flows into the system, and there we saw that whenever this U was increasing, then the number of possibilities were also increasing. So, and because what happens is that whenever you increase the energy, then the particles can have multiple states accessible to it, and therefore, there are more number of ways of doing it and S increases. So, that essentially is temperature, and we know that the temperature cannot become 0 or negative. So, therefore, it will be always a monotonically increasing function. Similarly, when you talk about U and V, we know that whenever V increases, U will decrease because and then only you will get a positive pressure on the system. So, whenever you have you increase the V, then the particles will separate from each other and the internal energy will decrease, and that will give rise to a positive pressure on the system. So, then that makes sense, and chemical potential is again by changing the number of particles, one can change the energy of the system. So, for example, you talk about a salt solution, so, and then depending on the water and the salt particle, your this thing will change, the energy of the system will change. So, thus we see that how this internal energy is related to these 3 different variables on which it depend on. Now that we talked about that, we can say that we can actually extend this particular ones to more than one component system, more than 2 component system and multi-component system, and in that case generally we can write U as a function of S, V and in I's, where I can go from 1 to the number of components, and in that case we can simply see that we can write du as del U by del S at a function V and all n i's, ds del U by del V at a function of S and all ni's plus sum over I del u by del ni at a function of S and V d ni, where which means that del u by del ni for a multi-component system at a function of S and V is nothing but mu I. Never forget these subscripts, because without that it will not be meaningful, and mu i's are just for a multi-component system, for a mixture of 3 or more components, each of them will have their own chemical potentials, and chemical potentials you will know in the later courses, we will not discuss in this course, is something like chemical pressure. Like for example, pressure equalizes the volume, the pressure is try to equalize and change the volume. Similarly, chemical potentials drive the change in the number of particles of different components and make the chemical potential equal between two components, and that is what we see in osmotic whenever there is a permeable membrane and there is a change in the component, and that is where the chemical potential actually play a role to change that across the membrane. Okay. So, now we remember, now we are going to discuss a new thermodynamic variable. So, remember that we have defined H as u plus P v. So, therefore, taking the differential in both sides, it will be du plus P d v plus V d p. But we know that du from our earlier example is T d s minus P d v from our equation 3. So, we can write that T d s minus P d v plus P d v plus V d p, and we get T d s plus V d p. So, you see natural variables of H are S and P. So, we can from here itself we can write that, okay, we are omitting the changes in number of particles from now onwards. So, we can write as del H by del S at a constant P is T. So, how did I do that? So, what I did here, I will just write it here. So, from this equation, which is let us say equation number, we have gone up to 4, you can call it 5. So, the way we did it is that we have dH is equal to T d s plus V d p. We divided both sides by ds, and we took the pressure constant. So, ds will cancel and pressure constant will become 0. So, that is what we get as T. So, that is what precisely we did that. We did not really differentiate, because already H is a differential amount. Similarly, when we do that with respect to P and take S constant, we get del H by del P at a constant S is V. So, you see that we are getting completely different different thermodynamic potentials using different expressions. So, for example, here we find that if we change the pressure and we see a change in the enthalpy when the process is done in an adiabatic condition and reversible adiabatic condition or called isoentropic condition, then that is nothing but the volume. Similarly, we see that if we change the entropy of the system and measure enthalpy at a constant pressure, we get nothing but temperature. So, some of the things may not seem very physical right now. However, you will see that some of the unphysical quantities can be mapped into something which is physical and measurable, and therefore, we need to know all these thermodynamic relations in order to understand that how to calculate each and every quantity is possible. So, now that I got that, we can now also write that in terms of something measurable quantities, and we can see that how this entropy depends on specific heats and things like that. We can write that as, again we are using the equation number 3 as du equal to T d s minus P d v, and now we can take V fixed and that we can denote by a subscript V. So, T d s V and dV will become 0 because we are using that. So, now at this stage we are going to take derivative with respect to t both sides. So, we will just do one more step, we will not jump here, we are dividing by t here. What we get? we get this kind of expression. We are dividing just by delta t on both sides and taking delta t limit to be 0. So, then this quantity that we wrote here, this particular quantity is what it is saying us, that there is a differential amount of change in u at a constant v for a change in t. So, that is precisely nothing but del u by del t at a constant v, that is what is meant. So, these writings are equivalent, and right hand side what we should write then, t, I have t only, and then this quantity, this particular quantity can be written as del s by del t at a constant v. Now, del u by del t at a constant v, you know that C v, that is called C v, right, specific heat at a constant volume, that is nothing but this quantity. So, therefore, we can write here that del s by del t at a constant v is nothing but C v by t. Similarly, we can use that expression of H also. We know that d H is T d s plus V d p. Again we take pressure as constant. So, we can write as T d s p, divide by temperature on both sides, we get T d s p by d t, and then we are writing it in a del form, giving us this one, and by definition it is C p. So, therefore, C p by t is del s by del t p. So, we got that C v by t, we got that C v by t is del s by del t at a constant v, whereas C p by t as del s by del t at a constant p. So, we have seen that how the changes in entropy with temperature at a constant volume and pressure gives rise to the specific heat divided by the temperature and all.